I hope you're here to learn about how you can use Wolfram Language for engineering, research, and teaching. Maybe you are Wolfram Language users already, or perhaps you haven't used the software before. I will hopefully cater to all of the above by not going into too much detail today and keeping it relevant for a wide range of attendees. So I will give you some background. I'm not an engineer myself. I have a physics background, specifically astrophysics. But as part of my job, I'm using Wolfram Language every day and always discovering new aspects of it. And this includes engineering applications. So let's go over our outline for today's webinar. By the end, I hope to showcase Wolfram Language as a complete, highly automated and integrated tool or platform inside which one could do some engineering computation. Okay, so I've got some graphic here which starts to indicate what I'm talking about here, whereby the things we're interested in doing in engineering, whether it's fluid mechanics, finite element analysis, kinematics, reliability analysis, etc., all come under this umbrella of computation. And that's what Wolfram Language is trying to encompass. That is essentially the ethos of Wolfram Language. We are trying to gather all algorithms, package them into these high-level functions, and enable this kind of computation. Okay, so I've got a couple of examples relating to different areas of engineering. Then I will talk about the Wolfram kind of ecosystem at large and how you can use these tools and how you can use some of our other resources to kind of improve your work. And then maybe we will get on to seeing the new Wolfram Notebook Assistant in action. So this is a large language model powered assistant to the notebook, which has been specifically trained to be highly skilled at Wolfram Language and can help you go from kind of zero to something that really works. Okay. I will also add that all the code you will see today is Wolfram Language code. And I'm doing this talk within a Wolfram notebook. Okay, go outside of full screen and you can see my cursor here. You can see that I'm in the Wolfram application. Okay. Okay, so the first example is related to computing a frequency response. So signal processing is very important in engineering, and we have a huge toolkit available for signal processing. Specifically, this example requires a link to what's called System Modeler. All right. Now, System Modeler is another Wolfram product that I can just drag across here, and you can see this is the interface for System Modeler. And this is for, you know, model-based systems engineering. And it has a drag and drop interface where you can build your own models and simulate them all within here. So I'm going to go into the built-in examples here on the left and maybe go into electrical engineering, DC motor, and then open this model. Okay, and as you can see, we have the model in the interface here. So there's actually a couple of views that System Modeler can have. I'm currently in the modeler mode, but you can also be in presenter or beginner. And things are just a little bit different. As you can see in the beginner mode, you have fewer items on the toolbar at the top here. Now, this isn't a tutorial on System Modeler, but we do have lots of resources on this, and I'll just drag this tab across. On WolframU, there are quite a few courses that are based on System Modeler, like this quick start, analyzing systems using Wolfram Language and System Modeler. And there's also study group sessions, which happen very regularly. Okay, so I encourage you to check this out. Great. So that's System Modeler. We are going to see how we can interface with System Modeler from the notebook, from the Wolfram notebook using Wolfram Language. Okay, so we can minimize this. This built-in function called System Models returns essentially a list of all built-in system models, and I've just kind of abbreviated the output here. So because this is the first system modeler-based function I'm running in this session, it just has to load a couple of the libraries and things like that. As you can see, if I hover over this cell, it is running. And here's a very short abbreviated list. As you can see, if I wanted to output everything, it would be over 7,000 elements long of the built-in system models. Okay, we can also do a kind of string search within system models. If we wanted every built-in model that had resistor in the name, I could just run this. Okay, and then you get some actual Modelica models. So if I hover my cursor over these kind of models, you can see it's modelica.electrical.analog.examples.resistor. And then you have all of these different types of resistors that maybe you could build these yourself off like the fundamental building blocks of the Modelica language, but these are pre-built such that you can develop kind of higher level models that just build on the things that have been built before. Okay, and then here's just another example of this, a random sample of all system models that come under the built-in fluid examples. Okay, so first it has to generate all of these examples and then pick essentially 5 random ones. So we have a tank controller, heat exchanger simulation, equilibrium drum boiler, one tank, and batch plant standard water. So yes, the models that are built in are not just the simple ones. There are, you know, complicated models that are just built in. You have free access to these to go in and configure them as you need, or just build higher level models that have these as kind of sub models. Just like how a code base can have, sub modules or subroutines or something like that. You can kind of plug different models into one another, and then all you have to check is that whether they can speak to one another correctly. Okay, so that was a introduction to System Modeler. I can also show you all of these functions. I can do a kind of Wolfram language function search of all of the functions in the language that include the word system model. And then this is the result. So some of these are like symbolic representations of what a system model might be, like a calibrated system model or or like some system model simulation data. But the rest are actual functions that you can use to interface with System Modeler. Okay, particularly useful one is this System Model Simulate, which we'll show below. This actually, provided you have System Modeler installed, runs the system model from the notebook. Okay, so that would be the equivalent of kind of pressing this play button, but you're doing it all from the notebook, and you don't even need to have System Modeler open to do this. As you can see, I can use this like drag and drop interface and kind of click into it, click into the different components and see that this DC motor is made up of all the things you'd expect: a kind of input voltage, a resistor, an inductor, a source of EMF, a speed sensor for angular velocity, etc., etc. Okay, but I think, yeah, I don't want to go into too much detail of what the system modeler interface looks like. Okay, so I'm just going to close this down and we can move on to our example. So as you saw that model within System Modeler, you're now seeing how the Mathematica notebook is kind of representing this model. So I can hover over it again, and we have well, what the Modelica name for this model is, and then we we kind of pass this to System Model Simulate. As you can see here, System Model Simulate needs a model, it needs a time uh, until which it runs a simulation, and then you can also provide it with some options, like here we've given it a sinusoidal input voltage. Okay, and we're going to run it from 0 to 20 seconds. So we've called this, we've just called this sim, given it the variable name sim, and we can run this now. So you can see the kind of training progress reporting here. It'll just tell you how far we are through our simulations, but thankfully it runs quite quickly. And then we have this system model simulation data object from 0 to 20 seconds. You can see that we have 54 variables, 11 parameters that we've got here. You can also be a bit smarter about this and tell System Model Simulate which variables you want to kind of keep track of. If you want to save a bit of uh, data storage, for example. If you have a huge model with like 2,000 variables, but you only care about, 5 or 6 of them, this would be something you'd do. And you can just check the documentation of System Model Simulate if you want to know how to do that. There you go. Stores only simulation data for the variables vars. Great. Okay, so now we've got this system model simulation data. We can kind of inspect it and see what was the result of this system model. And the best way to kind of interrogate a model is to plot some of the results, and we can use system model plot for this. So this just needs the simulation data, which is in sim, and then W is the symbol associated with angular velocity in the model. Okay, and you can pick these yourself if we wanted to, like if we wanted the angular velocity to have a different name within system modeler. When you're making your own model, you can just specify that, but in our case it is just W, I guess. W looks like the lowercase omega, so that's why it was chosen. Okay, so here's the system model plot. You can see this sinusoidal response of the angular velocity over time, very likely following this sinusoidal input voltage. Okay, so this is all going as expected so far. You can also plot multiple things with system model plot. You could plot lots of variables on the same graph. You can give it a legend. You can configure this just like you would all other plotting functions in Wolfram Language. In fact, let's just try this. There you go. So very small customization, but just to show that it's possible. Okay, now, given that we have this response of the angular velocity, we might want to kind of see exactly how this or how different frequencies respond to different input voltages, for example. And what we can do is plot a periodogram, which actually shows us something called the power spectral density of our data, in this case, our angular velocity, as a function of the frequency. Okay, so you can read about this in the documentation here. Um, but first, I'll separate this onto different lines, actually. So first, we create this data symbol by making a table of the angular velocity at different times. Okay, show you the first 5 elements of this. Check how long this list is. Okay, 200 elements, so I don't think I'll show all of them. Now, if I do list plot of data, it should give me something quite similar to this because it is just the same data. There you go. Okay, excellent. But periodogram will give us something different. So where we have a peak here, this is essentially a peak in the power spectral density. And what this means is that the motor's angular velocity was responding very strongly to the uh, input signal fluctuations at these frequencies. Okay, so at 1 and 4. So very important function in signal processing. And as you can see, all we needed to give the periodogram function was our list of um, angular velocities. And then the rest of this is well, just options, really. Options to help with the plotting of this periodogram. As you can see in the documentation, you could also apply periodogram to audio and video files that just integrate seamlessly into the notebook. I do have an example later on that is related to audio processing. So great. So there you go. If you didn't know about System Modeler before today, now you do. It's a very powerful tool and has uses, widespread uses in many different industries. I think I'll move on to my next example now. Uh, there's a section here on reliability analysis where it kind of shows off some of our like probability distribution functions. I think I'll leave this for you guys to go over in your own time because you do have access to the notebook. The link should be in the either in the chat on YouTube or in the side panel on Big Marker. So I don't think I'll go through this today because I want to go through the other examples. But yeah, this is there if you're interested in reliability analysis and how we represent kind of probability distributions in Wolfram language. Okay, so the next example I'll go through is all about solving partial differential equations over 3D regions. And the example we're going to look at is the bending of a spoon. Okay. I'll give you a bit of background here first. If I do a similar kind of string search as I did before, we can see all of our PDE related functions. As you can see, there are quite a few. Some of these are quite new functions, so have only come out in the recent versions, magnetostatic PDE component being one of them. But yeah, we've got acoustics, electrostatic, fluid flow, heat transfer, solid mechanics, Schrödinger, mass transport, etc., etc. And let's take the heat transfer one, because this will take us straight to the documentation if we just press the I. Look at the description here. Let's try and you know, approach this problem as if we are beginners. So what it says is it yields a heat transfer PDE term with variables and parameters specified. Okay, so this isn't solving a PDE or anything like that. It's kind of a constructor kit for something you plug into something like ND-solve or some other differential equation solver, right? It's a necessary component. That's why you've got this word component in the function. So it's a way to streamline the setting up of equations that will ultimately be solved using perhaps Wolfram's ND-solve functionality. And because setting up the equations is often the hardest part of partial differential equations, it does simplify lots of this work for you. And all of these different PDE component functions take the same format. They just kind of set up the equations in slightly different ways. So for fluid flow, you need to set up the kind of Navier-Stokes equations. For the magnetostatic and electrostatic, it's Maxwell's equations become relevant. And then Schrödinger PDE component, you obviously need the Schrödinger equation. And these functions kind of capture the logic behind the setting up of these equations and all of the subject matter expertise that is required to solve partial differential equations of each type. Okay, so this is really a aspect of Wolfram language to watch out for in all of the newest releases, because it's becoming really quite impressive and competitive with any other industrial partial differential equation solver out there. In fact, recently I was at the Wolfram High School research program, and it was really cool to see these high school students who hadn't necessarily gotten the experience solving partial differential equations before, but they could model behavior using these functions. Okay. And so they could get started using things like fluid flow PDE component or heat transfer PDE component. And then they could make some interesting visualizations. And then they could go into the exact mathematics behind it in their own research. Because what's really cool is that straight from the documentation, you can read these tech notes, and maybe you could go to a whole tech note on heat transfer, which gives you everything you need to know, starting from the very top. So starting from the heat equation in this case. And it will give you the relevant physics and engineering background, but also it starts to splice in some functions of how you'd actually do this in Wolfram language as you go through. Okay, so really, that after reading through one of these, you should know everything you need to know about, modeling partial differential equations in the area you have chosen. Let's say, yeah. Let's look at the fluid flow one. I'm a little bit more familiar with this, so I can go into the guide here, and then I can bring up the tech notes, laminar flow, and then we have this very extensive tech note all about fluid mechanics. Starts with a discussion of the Reynolds number, boundary conditions, how we represent these using vector plots and stream plots, how we can parameterize it, and then moving on to things like time-dependent Navier-Stokes, like as you can see here. Okay, so yes, I hope you find something useful in here, and you find a partial differential equation constructor function that is useful to you. Now, this example concerns the solid mechanics PDE component. As I mentioned, we're going to be bending a spoon. So, as I mentioned before, you need variables and parameters. Okay. So our variables are going to be u, v, and w, the displacement in the x, y, and z direction, and, well, also the variables x, y, and z. Okay. Our parameters, we are just going to specify that the material we're using is silver, and silver takes the form of a Wolfram Language entity here, where this entity has all of these physical and non-physical properties that are relevant for things like solid mechanics. Okay, so as you might imagine, if you're modeling solid mechanics, you need to know like the Young's modulus of the material, etc. But if you just say the material is silver, you can, well, Wolfram Language knows the Young's modulus of silver because it will be within its properties somewhere. As you can see, it is here. So I can just query this myself. Even comes up as like an autofill thing. 83 gigapascals. Okay, now you could say in the parameters, you could say Young's modulus goes to 83 gigapascals, but it's much simpler to say the material goes to silver, and then you let the solver or the partial differential equation setup figure all of this stuff out. Okay, so we'll evaluate these. So we have definitions for vars and pars. And then we're going to import our WXF file, which is our spoon model. Okay, so this is a kind of 3D object that we can interact with. And this is the thing that is going to be deformed. So how do we actually use these PDE component functions? I'm going to take you through this step by step. So as you can see, everything is wrapped within ND solve value. That's actually doing the solving of the partial differential equations. But first, we should actually talk about what's happening in these functions. Okay, so let's just evaluate this in a line on its own. As you can see, we've got lots of div and grad operators representing all of the equations you need to solve a problem like this. And you might be wondering, where are these numbers coming from? These 10 to the 11, 10 to the 10. Well, that is just because solid mechanics PDE component has been provided with this pars, which is the fact that the material is silver. So it's gone in and found things out about silver that it needs, like the Young's modulus. In fact, I'm pretty sure that this number, oh, I'm pretty sure that the reason these numbers are so large is because they're using the Young's modulus in some way. I think you also have something like the thermal expansion coefficient, which is some number in reciprocal kelvins. Okay, so it needs to kind of extract all this information to be used within this, like these vector calculations. Okay, so hopefully this is kind of nice. This is demonstrating that, it's not a black box. We can actually see which vector equations are being solved here. Now, notice that this is being set equal to something, which is the solid boundary load value. Okay, so what we're saying here is we're going to provide a boundary condition of where we're applying the force. Okay, where is this load coming in? And we can also run this on a line on its own. As you can see, it kind of takes our statement here. We're saying that between minus 0.05 and 0.05, we're going to apply a force of 400 newtons in the negative z direction. Okay, and this kind of splits, well, takes this, and when we run it on its own, we get some Neumann values, and then something that is a bit less legible, but this needs to be interpreted by the ndsolve value function. Okay, in a similar way, we have the solid fixed condition. So this is saying that everywhere else, except from where we're applying the load, we want to keep it fixed. So that is less than minus 0.05 and greater than 0.05. And now we have Dirichlet conditions for this. So this is nice. It shows that, technically we don't have to use solid fixed condition here. We could have just gotten there with Dirichlet condition, which on its own, that could be broken down into other built-in functions. But, we're kind of going higher and higher level all the time. Okay, so as you all know, in order to solve these partial differential equations, we need to have boundary conditions, and this is what they look like. You can also notice this OR operator, these two vertical lines. This means OR. Sorry. Okay, you can see in the drop-down, it's actually given the shorthand of these two vertical lines. So what I'm saying here is that x is less than minus 0.05 or x is greater than 0.05. One might be tempted to use the AND operator here, but you'd run into some trouble there because if you put AND here instead of OR, you would actually end up with errors because there are no instances where x is both less than this and greater than this. And the AND operator would take that very literally. Okay, so I think that's enough preamble. So yeah, that's our equation. They are our equations. The first argument of ndsolve value. So that's this equations here. Then we want the expression, and our expression is u, v, and w. And then finally, we have the domain over which to solve the equation, where we're saying x, y, and z are elements of the region specified by spoon. Okay? X, Y, and Z, we only care about what X, Y, and Z are doing as long as they are on this spoon region. Okay, and then we can run this and we'll get 3 displacement vectors, U, V, and W. It might just take a while. Oh, here we go. So we have interpolating functions of X, Y, and Z in all 3 directions. Okay, and now we can use vector displacement plot 3D to essentially plot the original spoon and the displaced spoon on a single set of axes. As you can imagine, this will take some rendering as well, so it doesn't run instantly. Here we are. So, after all that, you can see that we have a slight dip in the spoon between minus 0.05 and 0.05, just like I said. So it matches up perfectly to this solid boundary load value condition that we specified. And obviously the force is in the negative direction, hence the force on the displacement downwards here. So I think this is a really nice example. And And because you have the notebook, you should play around with the boundary conditions here. Okay, change this to, maybe you are just displacing this end, or maybe you are kind of twisting the spoon in some way. You can really be creative with this. uh, yes, and it will also give you some experience in how to properly formulate your boundary conditions in Wolfram language, which will be incredibly useful if you then go on to the other PDE components that we have here. So one last look at the heat transfer PDE component documentation. I would like to show this, although I won't go through the all of the code. Um, if I scroll down to scope, and then we can go into the 2D heat transfer examples, it actually takes you through this ceramic strip example where we have hot kind of outsides here, and it is dissipating heat into this cooler ambient sink. Okay, it's losing heat via heat convection and radiation. Um, and then we set up our region, we set up our equations. In this case, we have a parameter of thermal conductivity. Again, boundary conditions expressed very similar to our solid fixed condition and solid boundary load value, except we have heat temperature condition and heat transfer value, uh, and so on and so on. We use ND sol value again, and we have this temperature field as a function of x and y. So whilst this is all still very hot, 954 degrees Kelvin in blue here, hopefully this makes sense that obviously it's going to be cooler closer to the colder ambient sink. And in a couple of lines of code, we've gone from diagram of model to 2D contour plot of our diagram, where it is colored according to the temperature. So that was a whistle-stop tour of our PDE component functionality, but I hope it was useful. And yes, I hope to see more and more people using this, because it is quite an intuitive way of setting up the problem too. Similar to how you would, I suppose, if you had just a blackboard, except you have access to the tools of actually doing the computation incredibly quickly and efficiently. And that reminds me that we have a colloquium hosted on the WolframU YouTube channel, where some of you may be watching this, and it's numerical methods for PDEs and their applications. Okay, so we have lots of speakers here, people who are really experts in this stuff. Will be speaking about what's new with numerical methods for PDEs in Wolfram language. I'll move on to the next example, in which we'll be modeling the velocity of a rocket. So just like how we imported some 3D model of a spoon in the last one, here we're going to be importing some data into the notebook. Okay, and we're going to be solving this rocket equation where we have, well, it's a first order approximation to the velocity of a rocket. And we have parameters like the initial mass m naught. We have the fuel consumption rate beta, the exhaust velocity v sub e. Okay, we're going to assume we don't have a exact analytical solution, and we want to essentially fit this data in the file rocketdata.dat to find a good value for beta. Okay, so what this is just time velocity pairs from 2 seconds to 60 seconds. Okay, as you can see by the end, this rocket reaches a velocity of almost 1,000, I guess it's meters per second. Yeah. Okay, so what we're going to do is just take this differential equation setup where we have our equation and then our initial condition of v0 is 0 and express it in Wolfram language terms. So here we can just use v prime, indicating that it's been differentiated with respect to time once. We can use our beta, our value of VE, our value of M naught. Initial conditions go here, and we want to solve for V between time is 0 to time is 60. And this last section is very important because we're leaving beta as a kind of free parameter. All right. So notice we haven't used any data yet. We are just setting up the solution as a parametric function of beta. There you go. You can see a bit more information in the symbolic parametric function object here. Okay. Now we're actually going to bring in the data here. So we're going to take rocket data and fit our model for V to this data using this nonlinear model fit function. Okay. The function quiet is wrapped around here because there are some errors in solving as you approach this kind of 60-second mark uh, that I just want to suppress. So yeah, quiet is a way you can do that. And this symbol here, replace all, this slash dot is just telling well, what it's doing is replacing V with our soul. Okay. Suppose I could run this. So it's just saying wherever you see V as a function of beta and t, you replace it with this parametric function here. Okay. So here's our fitted model. And then we can visualize the fit, including our actual data on the plot as well. Okay, and there it is. So the black dots here is our data taken from here. And the blue line is our fit to that data using this parametric function. Okay, and then we can also query this fitted model. This fitted model has all sorts of properties, such as the ANOVA table, the parameter table, and the parameter bias that we can find out. And we can just get a list of these things. You could also find out some other properties just by saying properties. As you can see, there's lots going on here. I think there is an update in version 14.3, which is yet to be released to the public, but it's coming very soon. Yes, there's an update of our model fitting functionality. So I think there is potential to fit more kind of nonlinear models like sinusoids and things like that. And it's been greatly improved upon. So that's another thing to watch out for. And then finally, we can plot the residuals at all times here. So from, well, this is showing to 30 because there are 30 data points, but every data point represents 2 seconds. So that's why it's not plotting against time here. It's just plotting against the number of points. And as you can see, some of these are reasonably large residuals, I guess, but we don't see any systematic error here. It's kind of scattered around 0. So this is the sign of a good model fit. Great. So yeah, a nice little introduction into our solving and model fitting capabilities. So we saw nonlinear model fit here. If you scroll down to the bottom of any documentation, you can see the functions that are like related to it. So you have linear model fit, generalized linear model fit, time series model fit, etc. Let's have a look at generalized linear model fit. Least squares, obviously very important. Um, yeah, so very well documented this nonlinear model fit. You have, lots of examples of fitting to data and querying for the properties, just like we did with our residuals. You could also have standardized residuals. Um, Someone has asked, Indranil has asked on YouTube, are you using Jupyter and Python? The answer is no. Oh no, he asked, are you using Jupyter and Wolfram? But no, this is all taking place in a Wolfram notebook. Okay, or a Mathematica notebook if you're more familiar with that. So yeah, this is the desktop application is a Wolfram notebook where you can integrate text, graphics, images, video, audio, and obviously your code. In fact, I mentioned the summer research program earlier, and every one of the students produced a kind of Wolfram community post, which is another way in which you can kind of share your work that you've done using Wolfram language. Um, this is a very impressive project on a prosthetic hand. And every one of these community posts is itself a Wolfram notebook that is just hosted on the cloud now. So if you read these Wolfram community posts, you can download the notebook and then run the code on your desktop, or you can just um, read the notebook on Wolfram Community. But yes, this is all done in Wolfram notebooks too. Okay, I mentioned we will do another kind of audio signal processing example. This is this is a the whole basis of this example is a 5-second audio um, file of a car speeding past an observer. Okay, um, I'm going to play the audio, and hopefully you'll be able to hear it too. Okay, so a classic example of the Doppler effect, where you have changes in frequency according to whether the source of the sound is approaching you or receding from you. And we can use all of our built-in audio processing functions on this audio file. Okay, so we've called this audio file vehicle sound. So we now have a variable that is vehicle sound that, if I run this, I just get the um, audio file again. I can find the byte count of this audio file. I can show that the head of this audio file is audio. Okay, makes sense. Okay, so we want to extract some frequency data. Uh, so we're going to use pitch recognize on the vehicle sound to run this in another line. Okay, so this splits the audio file up into small timestamps, it seems, and then the pitch or frequency that it's recognizing at each one of those time steps. Wonder what happens if we... Okay, so if we remove the path kind of specification from this, we just get a time series, as you might expect. Um, so yes, querying this for its path takes our time series, and instead of a time series, we have a list of 211 data points. So this is something that can be plotted using list line plot. Again, we can style this however we like. Let's say green. We can add axes labels. Usually the X label first, then the Y label. Let's say time, frequency. There we go. Okay, so this is the plot of frequency with time, and we want to, we want to extract some information from this this data, right? So what we're going to need for that is the formula for the Doppler shift, and we can do this. We can go into the Wolfram knowledge base and find the formula data of Doppler shift. If we didn't know exactly what to look for, we could use something called formula lookup, and then formula lookup is a kind of less strict version of formula data where you just give it a word, something that you think is close to the formula you're looking for, and it will return all formulas that are related to this word. So as you can see, we have lots of Doppler shift formulae, and we wanted this one. Okay, so then you just paste this into formula data. Okay, if I wanted, I don't know, the formula for a Lorentz transformation or something, we could look at this. Yes, lots you can do with formula data. Okay, so let's run this. Here's the formula, and then here is the quantity variable table. So a bit more of an in-depth look at each variable in this formula. So we have the frequency reduction factor, which is dimensionless. We have the speed of sound, which obviously has units of length over time, as does this speed of the source away from the observer, v sub s. Okay, so we just recreate this formula as a kind of model where, yes, our observed frequency is just this formula solved for f naught. And the relative velocity is, okay, yeah, we're assuming that the vehicle is traveling in a straight line, so yeah, this is the derivative with respect to time of this kind of displacement of the vehicle. Okay, so we've got two formulae here: the observed frequency, which we got using formula data, and then the relative velocity, which we've got by making this kind of basic assumption that the vehicle is driving in a straight line. And then we can kind of put these together in our model. So we're going to say observed frequency, where we're leaving f as a parameter to be determined. We're saying that v sub r is 0. we're saying v sub s is our relative velocity given by this formula. And I'm going to put these on a different line just to make it easier to explain, but it doesn't matter. Wolfram Language indentation does not matter, so this is fine. And then we have this parameter c, which is just our speed of sound. So we're going to just get the speed of sound from the Wolfram knowledge base. Okay, let's run this to get our model. So here, 340 meters per second is the speed of sound, and then it's essentially just inputting these formulae into this model, because we don't have numbers for d, t, t naught, v, and f yet. If you're having trouble to like make sense of this formula, just think of, I've got this image that might help, just of this car that is, well, traveling in what's called a rectilinear trajectory relative to the observer, where you have a fixed distance away, so that would be kind of into the screen here, and then obviously as time passes, the distance, well, parallel to the plane of the screen, or in the plane of the screen, would be changing. Okay, so that's all that's going on here. It's a basic relative velocity formula. Okay, so again, we're going to use nonlinear model fit here, using our frequency data. So what is plotted here? We have our model, so we're going to fit the data to this model, and these are our variables or parameters we wish to fit. So we have f, we have d, the distance to the moving vehicle at closest approach. We have v, which is yes, the speed of the source away from the observer, and we have t naught, the time of closest approach. Okay, you might be wondering why this f is in a list with the number 200. This is because we are giving nonlinear model fit kind of the first value, or a kind of starting value to look for the optimal value for f. Okay, so we're kind of saying start looking at 200 hertz for the value of f. Okay, so we have a fitted model. And then we can check how good this fit is. So the blue is the fitted model, and then you can see in gray, I might just make this black so we can see it a little bit better. You can see the actual data very close to the fitted model at every time. So this model has worked. It's a successful model. And the only thing left to do is to find out, okay, which values for f, d, v, and t naught were actually found. And we just lay this out in a grid. Okay, so we have a base frequency of 350.8 hertz, a velocity of 20 meters per second. It was the distance, nearest distance to the observer of about 5 meters. So maybe this was, a police car at the side of the road that was monitoring the speed of cars passing by. 5 meters, I guess, is quite sensible for that. And the time at the nearest point, so 2.55 seconds, so almost exactly in the middle of this audio clip that was 5 seconds long. Great. So kind of a similar example as the rocket data one, but a little bit more, well, insight into how you can use the built-in formula data that we have in Wolfram Language too. One more thing I wanted to show that very useful with formula data. So you don't actually need to give it an option here. You can just say formula data Doppler shift, and then you can start to put values for the variables here. So I can say that I want the value of 340 meters per second for C, and then I can run this again, and it will input that for me. Um, However, I can also give a value for VS here. Okay, so maybe I want this to be speed of the source away from the observer. Let's just give around 20 meters per second, like we found from the model. Okay, so what's nice here is that it's done some simplification, and we can actually get a value for F naught over Fs. And this is very useful. So we can apply it to a completely new example. Let's see if there's any formulas relating to black holes. Hmm, or maybe Schwarzschild radius. Okay, let's simplify things a bit. Let's just look for formulas related to radius. Okay, I'm going to use this one. Okay, so this looks like what I was looking for, the Schwarzschild radius of a black hole, where if we start to input some parameters like m goes to, let's say, 1 solar mass, then we can actually get a value for the black hole event horizon radius in miles. But, you know, we can just say the unit system goes to metric to change this, and then we have it in kilometers. Because the system is entirely determined, or this equation, sorry, um, is entirely determined by the mass. But yes, I know I'm at risk of straying into physics here. But yeah, I think this formula data is really useful. I mean, all across education, teaching, um, I think this formula data function and functionality is criminally underused, let's say. Okay, so I did take a while to go through that example, so I think I'll finish this talk with more of a discussion on research and teaching and the needs of both of those. So, having been at university only 2 years ago, I know that when you're conducting your own research, you want to be able to quickly explore ideas, you want to develop the solution easily, and you want to clearly present those ideas to, supervisor, uh, course mates, etc. And you want to spend less time on the implementation of your solution and more time, thinking about your solution and then deriving some interesting insights uh, about your result. Okay, so this is the kind of perspective of the researcher, but also as the teacher, if you're teaching something, you want to be able to explore ideas quickly and you know develop a solution that makes intuitive sense to your students and clearly present this solution to your students and and say, this is how you make a uh, stress strain model of a wire or of a beam or something like that, or this is how you model the heat transfer of a a ceramic strip, just like I was showing before. And Wolfram Language is such a powerful tool to quickly explore these ideas, development of a solution, and presenting the ideas, of course. And that's why we call it the ideal teaching platform. That's why we say that Wolfram notebooks are the ideal teaching platform. You can have computation, interactivity, and narrative all in the same place, um, as as I've shown today. Okay, I've given this entire presentation from a Wolfram notebook, as some of you asked about. Yes, so I can, speaking from experience, I did use Wolfram notebooks during my studies to submit coursework and gather my results, make plots and visualizations for my condensed matter physics modules, and write about what I thought the plots were saying underneath, that kind of thing. Um, Now, another very solid option for work like this, and obviously university work and writing reports and things, is to use LaTeX, is to use Overleaf, um, which I've used before. As some of you maybe you're already familiar, but yeah, Overleaf is a very popular typesetting system that uses LaTeX. But something I've been discovering recently is that we have quite powerful support for LaTeX using, well, in the notebook, in the Mathematica notebook. So if I'm in a new cell, I can type. I'll type what I'm typing actually, because I just have to leave full screen for this. You type Control 4 on Windows. You have this input cell that says enter a text string, and you can actually write LaTeX directly the um, into the notebook. So maybe I'll write something like, okay, something like this, and just click out, and then I have this LaTeX formatted square root of a over b. So this is very nice, and I've used this for quite a few things when presenting work that I've done in the notebook. Another option is to use a built-in function that we have called TeXForm, which takes some Wolfram language, for example, this a plus b squared, and then gives you the LaTeX typeset expression of that Wolfram language expression. So we'll just test this really quickly. I think this is really nice because if you're used to Wolfram language and you want to know how to write this in LaTeX, then you can use this TeXForm function. And yeah, there's a little bit more on this kind of documentation page on how you can use this integration. Writing a matrix, for example, and an expansion, and you can see here that the expand function is run first. It's kind of run from inside to out. So it will expand x plus y cubed first and then show you the text form of that. So yes, some people often think that we don't have the LaTeX support, but evidently we do. So if that was a barrier to using Wolfram notebooks for your work, then hopefully that's been squashed. Okay, and then something else that is also accessible via the notebook is access to chat-enabled notebooks, where instead of code cells, you can have chat cells. So here you have like a chat cell that you can configure to call on an LLM of your choice. If I go into my settings here, I'm currently using the kind of built-in Wolfram Notebook Assistant and LLM kit, which is kind of choosing which model to use for me. But I could, in principle, just choose any one of these uh, large language models to help me write my code. And we also have an LLM benchmarking project where we kind of test to see which LLMs are best at writing Wolfram language code. And you can see that here. So currently the Claude 4 Opus is the best. 99.9% correct syntax. Wow. Uh, Last updated July 16th, so only a week ago. So this is important. This is somewhere that you should keep checking out. But yeah, that's what the chat interface looks like in Wolfram. And it's what's really nice is that you'll get code that the uh, large language model might generate. Uh, let's say um, go me an interactive illustration. The code that it generates, you can just paste directly into the notebook. You can insert and evaluate even. Okay, so I've got a nice demonstration of beats. Very impressive, actually. I like that. And obviously, it's used manipulate here to make this nice and interactive. It probably would have done this anyway, but using this prompt word interactive often helps you know guide the large language model to use things like manipulate. Um, yeah, excellent. If you wanted to interact with large language models more programmatically, we have all of these built-in functions like LLM function, LLM prompt, LLM tool, which are all built in. You can check the documentation just like you can with other functions. So yeah, what follows is a look at some of our other repositories and resources. This one is from Wolfram Demonstrations. So if you go to demonstrations.wolfram.com, you can find lots and lots of examples. Here we're looking at feedback control in a stirred tank reactor. So we have lots of sliders we can vary here, and you can every example on demonstrations is using a manipulate. You can follow this link for more examples on that. We also have the Wolfram data repository, which I've found has got really cool examples related to engineering. We have models of helicopters, double pendular. There's even a model here of a satellite, I think, of the attitude dynamics of a satellite, and then it often gives you kind of a starting example in the analysis section, but you could expand upon this further if you wanted. Um, yeah, but yes, lots in the data repository and lots of specifically engineering examples too. Um, it will also tell you how exactly to retrieve the model into the notebook just using this resource data function. So yeah, I could show you exactly what this looks like. So it's finding the resource, and then it's just now we've got the nonlinear state space model corresponding to this quadcopter, which is fantastic. Um, great. Yeah, we can access Wolfram Alpha straight from the notebook too. So if you didn't know exactly the Wolfram language input, you could just ask in natural language, and Wolfram Alpha will figure it out for you. So here we're getting a kind of transfer function. Um, Lots of information on this because we're getting a Wolfram Alpha long input. If I just type equals, this is Wolfram Alpha short, but then if I type 2 equals, we get a Wolfram Alpha long input. Okay, you can also look through these step-by-step solutions, but I've kind of already talked about this when I discussed the formula data, so I'll move on. And I've mentioned Wolfram Community, where things called computational essays are published. Many examples of which can be found on Stephen Wolfram's Writings website. So yeah, I'll leave the conclusion slide up. I've got some next steps. Someone said, will compatibility with LaTeX be developed? Is there a way to convert whole LaTeX files to Mathematica? Okay, so someone obviously very interested in the LaTeX integration. Because I work on the consulting side at Wolfram, I'm not entirely sure of what are the current developments of our LaTeX integration, but can find a little bit more on this documentation page that I was looking at before. So I just saw this export string example where you can give it um, some traditional form, and then it will generate a compilable tech document. But I suppose you're asking about kind of going the other way from LaTeX files into Wolfram language files. Hmm. I did notice as well that at the bottom of this we have some functions in the function repository. So you have LaTeX preview here, which is rendering LaTeX as an image, which might just help for kind of um, visualizing what your LaTeX string would look like. But it does say here that it uses a third-party API. And there's a longer kind of tech note here about importing and exporting tech expressions. So to answer your question, honestly, I don't exactly know what the current developments are, but if you wanted to get in touch with like Wolfram support or make a recommendation, I'm sure there are lots of ways you can do this. Even if it's joining the live streams, okay? Join Stephen Wolfram's live streams and make a suggestion, because he will read them.